Hello, everybody. My name is Thorsten Anger. I'm a product manager at LUMILEDS. And today I'm very excited to talk about expanding the horizons of car body lighting. In recent times, a new application field in automotive lighting has entered the market. Many new lighting applications are entering, especially the space at the front of the car, and we call that car body lighting. You can see here a vast variety of different designs, and this is very exciting. However, it puts the engineering effort under very much pressure because all these designs and applications are peak solutions, which are hampering the carryover to the next platform, and currently are very limited to small volume vehicles. Now we, LUMILEDS, as a light source manufacturer, is thinking about how can we contribute to these new exciting applications with light sources, enabling reducing the complexity of the architecture. As a first step, we analyzed the existing and potential also new designs, which in automotive are normally displayed by concept cars, into different clusters to analyze what kind of light source would really support these designs. And as a result, we have identified three clusters. The first one consists of singular optical lit elements resulting in 10 to 50 light points in the front of the car, where light sources illuminate light guides or light pipes or light blades or reflector cavities individually. These are, as you can see here, from an application point of view and design point of view, completely different structures, but the basic architecture is very similar amongst them. Or as a second cluster, you have backlit optical surfaces, where optical elements are behind flat or smoothly curved A surfaces or complete body panels. You see here some examples of it. Typically, the light source number ranges from 25 to even more, several hundreds per car, as you can see here. Also, the light points are rather small compared to the other clusters. And then the third cluster is 3D illuminated structures. So homogeneously lit 3D optical elements for either direct view or with indirect and reflective optical elements, achieving a true 3D effect. So this is, of course, very special designs resulting in completely different applications. We had a closer look into some of these applications. So here on the left-hand side, the singular optical lit elements, we've chosen this application. There we have seen that there are around 50 light guides powered up by single mid-power LEDs. Each of these light guides is slightly different, resulting in different toolings for each of the light guides. The LEDs, of course, must be placed on a surface. Here in this case, it is realized by 3 flat PCBs on the lower edge of the light guide to accommodate the LEDs, and they all need to be, of course, enclosed and protected against the environment into individual luminaires. The total electrical power of the whole application is about 30 watt. Then we looked at two backlit optical surfaces. So here it's a wide curved grille, so it covers the whole front of the car and follows the contour of the car also towards the sides. There are hundreds of single optical elements, each one of them requiring individual optics, and each of the light points is lit up by low power LEDs. The strong curvature and the huge surface of this structure requires then either many rigid PCBs or huge flex PCBs to host the LEDs, which makes especially the integration, the mechanical assembly, very challenging, and will be nearly impossible to realize that with an automated industrial footprint. The total electrical power for this application was identified at around 15 watt. And then finally, looking at 3D illuminated structures, you see that there are complex mechanical structures to enable a true 3D effect. So they have, they are not flat, they have depth to realize the 3D effect, and provide quite a lot of space in the front of the car to realize that. The total electrical power of such an application is assumed at about 20 watt. Now, for all these different applications, LUMILEDS tried to identify general application requirements for dedicated light sources enabling an economical breakthrough. So if you look at the requirements, then if you look at the size of the complete lit area, so we've seen that this ranges from 40 to 160 centimeters in width. 160 centimeters would result in the complete front of the car. Heights are ranging from 5 to 40 centimeters. And depending on the overall surface, you have either flat or widely curved elements. The maximum installed electrical power ranges from 10 to 30 watts. This is an important parameter because especially electrical vehicles have only a limited electrical power budget, and that must not exceed it. The system efficiency, so the optical system efficiency, how much watt is translated into lumen, depends, of course, very much on the design requirements. Some applications on purpose allow to see the optical structure. Others, on the other hand, want to achieve a sort of wow effect, where in an unlit stage, the optical elements are hidden by a dark cover lens, and that of course absorbs much more light than with direct view. So that's system efficiency, very much depends on the design requirements. The overall brightness ranges only from 1,000 to 3,000 candela per square meter, so there is not so much flux requirements. Applications ranges from 10 over 50 up to 1,000 lit elements. So basically, very few big lit elements towards many very small ones. So, and that's also translated into the luminous flux requirements per light source. Must be also very flexible. So we try to visualize this in this graph here, where obviously if you have only a few light points, then the flux per light point must be rather high. So we think 50 should be sufficient. If you go to 100, then the requirement for each light point might be only at around 10 lumen, and if you go to several hundreds, then only 1 or 2 lumen per light point are required. Yeah, otherwise, the whole application would be just too bright, and you would not see the effects of it because it would appear only as one big light source. Now, there are also other technical aspects which need to be considered, especially when it comes to mechanical integration. That must be the complexity must be reduced so that the mechanical assembly can be realized with the help of automated machines, just to reduce cost. Also, the electrical interconnection between the light points, especially when considering single addressability, is for sure an attention point. Furthermore, the replaceability and modularity of the light source must be considered. Just think of a situation where you have a huge front car body lighting, and there will be minor damage at this element, and it requires an exchange. Nobody wants to replace the whole front of the car, so it would be preferable that only the damaged elements can be exchanged. Yeah, otherwise, the follow-on cost for the end user will be far too high that these applications will have a vast breakthrough. The environmental enclosure needs also some attention. So LEDs as electrical components need to be protected against the environment in vehicles, and enclosure always requires space. And it results in cost. So if this can be reduced, then for sure this is an advantage. And when talking about applications in the front of the car, which we are focusing here, then also other aspects like crash impact and pedestrian safety need to be considered. So the recent applications which we have seen always need to consider additional space for the application to generate safety for pedestrians and crash impact. So that makes it a sort of movable element. So if this can be avoided, that would be a huge cost benefit, and also from a BOM perspective, but also from an engineering effort. Coming back to the luminous flux requirements, we have built a demonstrator basically also to prove ourselves that, let's say, this curve is somehow valid. We built a demonstrator consisting of 192 individual addressable light points. So we are in the range of this curve, and we analyzed what kind of light source from a flux perspective is required to achieve either position light or DRL light. This demonstrator, as I said, consists of 192 different elements, and each one of them is single addressable, so that exciting patterns can be realized with smart software, which is for sure demanded by the market to achieve that. When looking closer into our demonstrator and to see what kind of elements we have used to realize that, but also to look into the aspect of using these elements again and again. Yeah, we have chosen a low power LED. I will come to that aspect on the next slide. As said, each of the lid elements is individual addressable for a vast variety of dynamic patterns. The LEDs are placed on three, you see here the structure from the backside, three rigid planar FR4 boards, with different orientations with respect to the axis of the car. With this demonstrator, we also wanted to prove that it can realize DRL performance requirements, DRL, daytime running light requirements. So each of the lid elements require a certain optical structure to support the beam requirements for DRL. And they are having a collimator lens for uniform appearance and to bundle the light. As you can see, the optical elements are always the same in the outer shape of a triangle, but also from the internal structure, they are the same. You can guess it from this picture. In the front, we have a diffuse film cover for smooth appearance and to broaden the bundle. The orientations of these repeating cells follows the contour of the car, so that the smooth lid appearance is not only visible from the front, if you stand in front of the application, but also if you walk around the application, that from any viewing angle, it looks always homogeneous. Now, when it comes to performance, to prove DRL requirements, each one of these LEDs provides 25 lumens at the full drive current of 75 milliamps, resulting in 29 candela peak intensity from each LED. And to achieve DRL performance, around 60% of the LEDs, which are facing towards HV, or front of the car, are required to be on to meet DRL. So this is then a light source, low power light source with 25 lumen for DRL. If we go for position light, then for sure 25 lumen is far too much flux, and even lower power LEDs can realize a position light function. So to achieve and to support the design of applications with many small light points, LUMILEDS is introducing a new family of low power LEDs, which we call Versa 2016. So this expands the range of our Versat family into the low power range. There will be two different types. One, a 0.2 watt device with provides around 25 lumen, which we have used for this demonstrator, which is available already right now, and a 0.1 watt device resulting in around 10 lumens, which will be ready for mass production and automotive qualified early 2025. Beyond the pure low power requirements of these applications, we think such a new LED must also provide some further support to the design, and one of them is the flexibility in the emission spectrum to support the design requirements. Just imagine the LED and the optical elements are placed behind a strong absorbing cover lens, which of course also influences the spectral emission of the light source. And if one wants to achieve still a bluish look, the light source itself might need to emit light outside the ECE allowed color box, and in conjunction with the application, it will shift the spectrum back to the allowed ECE white. Now this can also be transferred to the other side of the ECE white, where maybe applications shall distinguish from the typical bluish LED look, and where like warm white in the range of 3500 Kelvin or even 2700 Kelvin are required. Furthermore, this light source must be also very compact, and that's why it has a space requirement of 2 by 1.6 millimeters, hence the name 2016. And only a Z height of slightly above 0.5 millimeters. This is very important for optical design in. It reduces the dependency of the tolerances in optical coupling elements, especially if you have many of them. The mechanical and optical tolerance change is then less risky. And this is, of course, very important for these kinds of applications. Now, this new light source supports applications with many small light points. LUMILEDS has also an additional light source, which supports long and slim light lines. It is called Luxion 3D LED. It is in the market already since 2022. And you see here two applications where it's been used. The one is the Audi Q8 e-tron here above the grille as a position light function, or in the Hyundai Grandeur, where it serves stop and tail light function. As you can see here, it not only supports straight lines, but the lines can also be or have all sorts of structures. It is a very compact light source to support the space constraints which you find in the application, and it on its own is super homogeneous, so that to achieve the typical homogeneous requirement, no additional optical elements are required. This light source will have an upgrade next year with reduced performance to make it best economical fit for position light functions, whilst maintaining all the other properties of the super homogeneous and compact light source. The new version will be then called 3D LED light. Furthermore, we are working on a new concept which we will call MAX. It might enter the market and ready for mass production in 2026. It will be less compact and it will be less mechanical flexible, but it shall support straight line designs which covering the whole front of the car, and it shall support also the integration into the application in a different way that we have realized it with the existing versions. This is still under concept, so the design still might change, but that is then streamlined, especially for these kind of applications. Now, the 3D LED is for sure a typical modular light source with more or less one design, and but this one design is not limited to one application appearance. When combining the 3D LED light source with optical elements, it unveils its full design flexibility. Yeah, so for example, we have built this demonstrator in red where you can see that the light emitting width on the one side is very narrow. It broadens towards the center, then it becomes narrow again, and it has a curvature, and again, the light emitting width is flexible. And still, this application looks super homogeneous, and that is realized. You can see here a cut through the application, where the 3D LED light source is emitting upside down into a white reflector, collecting the light and then emitting to a scattered and textured outer lens to make it super homogeneous. But this light source can also be combined with many other optical elements. So we cluster them for collimating. So if the light shall be, the emitted light shall be bundled, and it can be done with indirect mirrors, or direct curved mirrors, direct straight mirrors, combined with lenses, or even lenses with mirrors. All of them will collimate the light in a different way, and which one can be used depends, of course, very much on the space which is available, very much on the intensity of the application which is required, and mostly how does it look from a design aspect. You can also combine it with other optical elements, especially when you talk about low intensity applications, like in our demonstrator, which fulfills tail function, like as we've shown here with indirect white reflectors or direct white reflectors, even using the 3D LED, powering up light guides or light pipes. You can also have them in combination with elements which scatter the light, so flat lenses or films with textures or even micro lenses, sculptured inner lenses with scattering surfaces or scattering structures on optical lenses. So the possibilities are nearly endless, how to combine this light source with optical elements to achieve different types of optical requirements, and especially design requirements. So next to small light points and next to long light lines, LUMILEDS is working on a third light source which supports larger optical surfaces, which we also see in the market. We call this the coin concept or coin design, although in these pictures you see that it is more square-like, but we started with the coin. The idea is to have a few different mechanical or structured light points to serve different applications. So just to give you an idea about how we want to realize that. So we have here the LED emitting into an optical layer, a first layer, and then a second one, which has diffusive properties to homogenize the light. These two optical layers are made out of soft silicone to support the aspects of mechanical integration, as well as what I talked earlier about requirements with respect to crash impact and pedestrian safety. They are then enclosed by a hard material, which acts also as a reflector to make it also more rigid for mechanical assembly. The top silicone layer shall have damping elements which can be used to compensate for mechanical tolerances within the mechanical assembly. The electrical interconnection could be realized either by traditional solder pads for SMT assembly, or with cut crimp connectors to connect to wires directly. So upon simulation results, we try to investigate how big such a coin could be without making compromises on the homogeneous appearance and emission of each of these coins. Of course, we also need to consider that the depth is a very important parameter, and it must be as compact as possible. Creating homogeneous light sources where the depth is endless is no real challenge, but with a compact depth, that is very well a challenge. So we have here a depth of only 8 millimeters, and then changing upon the optical layers I just described, and optimizing them, we can achieve surfaces up to 20 by 20 millimeters per coin with excellent homogeneous appearance, as you can see here. Yeah, obviously, at the very ends, this drops down, but we think from an application point of view, this is barely visible, and that such light sources can support then larger surfaces. I think this is could be a contribution to the requirements of these new exciting applications. So to summarize, we see that a new exciting applications in car body lighting are entering the market, obviously, and especially at the front of the vehicle, and the new electrical vehicles support that, where the grille, the traditional grille, is as its original function becoming obsolete. For the car designers, this provides endless possibilities to customize each of the applications, but from an engineering perspective, this can become a nightmare, resulting in peak designs with huge engineering effort, high tooling costs, and as a result, hampering a fast and economical cross-platform rollout. So at the moment, this is only limited to small volume vehicles and expensive vehicles. We think as a light source manufacturer, we can contribute to mainstream market adoption by providing new and smart light source solutions to the market to serve the economical breakthrough. We as LUMILEDS offer a vast and broad portfolio to support the car body lighting with optimized light source solutions, with scalable emitter flux range, with color tuning possibilities, and with miniaturized LED packaging and smart modular solutions, accommodating easy integration, all resulting in economical feasible solutions supporting mainstream market adoption. And with that, I would like to close and thank you for your attention. If you're interested in our products or want to know more, then please do not hesitate to reach out to me at Thorsten.Anger@lumileds.com. Thank you very much.